Welcome to class, everyone. Just have a few administrative things to talk about really quickly. First, I want to make sure and point out that there are new links in the textbook and assignment section. These should work. When I go through my student portal, it takes me to the correct place. So when you get a chance, if you haven't tried since, I don't remember when I put these on there, since yesterday, make sure and try again. And of course, just send me an email, because if it's still having trouble, that means that there's a different issue going on than what was going on before. So make sure and let me know if you're not able to access that introduction assignment. I keep moving the date out, and I'm going to keep moving it until everyone's like, hey, I got it. So try to access it if you can, get it done. If not, let me know. Yes, ma'am.
So
Say again?
you're not going to take the points off for that?
No, not at all.
Okay.
So if you haven't done it yet, then no big deal. And if you're late doing it, it's fine. Once everybody is able to access it, then I'll be like, okay, here's the date when it was due. So you're fine. In fact, let's just go in there. If you have to send me an email describing a problem, please describe the problem. I got an email that said, I can't get in. And I'm just like, okay, at what point do you get resistance? They're just like, I can't do nothing with it. No, I have no idea what the problem was. Let's see. There you go. I'll put this for Thursday right now. So like I said, try to access it. Also, some good news. Don't forget, you got your journal entries due every Friday. You'll notice journal entry number 2 is there. It asks about the Egyptian pyramids. It asks to relate them to astronomy. If you type in relate the Egyptian pyramids to astronomy, you'll get some information. There's also some words you might need, such as non-falsifiable. Please learn that word. So you can do it. Pretty fun. Then 10 minutes or so and get those points. Also, in your lecture slides, you'll notice the first day of class's lecture slide, the second day of class, which would have been Thursday day of class. So feel free to look at that. And this is today's. Also, if you go in the lecture video section, you'll notice this was last Tuesday. We were here. This is last Thursday, right? There are 2 lectures per week. Day 1, which I guess is Tuesday, and day 2, which is on Thursday. Since we don't meet on Thursdays anymore, you may want to watch this video. This is just me standing up in front of the class for an hour and 15 minutes talking about stuff. The Thursday classes, they were here, so they know this, so they got to watch this one. After today's lecture, a new video will pop up. A video lecture that says week 2, day 1. So make sure and check out the days when you are not in class. First, winter observation calendar. So I think that was all of the administrative stuff I want to talk about. So I'm going to pick up right from Thursday's lecture. This will be another benefit for checking out those videos, since I'm just going to assume everyone was here for all of them, hence the hybrid nature. So I'm going to pick up from Thursday's lecture as soon as I find it. Nope, wrong one. Awesome. So what we talked about is we talked about the speed of light, we talked about some of the great distances, and we talked about how we would measure those distances. One thing I do want to specifically say to make sure that it's on every video ever is to say that a light year is a distance. Please be aware, a light year is a distance, not a duration of time, right? So you can't measure time in light years. A light year is the distance that light travels in 1 year, which is 9.46 trillion kilometers. More information about that is on week 1, day 2 video. I just want to make sure and say that again. But for today, I want to start talking about discovering the universe for yourself. So in order for us to do that, we have to first figure out where we are and where we're going, right? You gotta know where we're starting. So let's start with this. The Earth is always moving. Now we know that the Earth rotates once every approximately 24 hours-ish. Is it exactly 24 hours? No. We know that the Earth orbits the Sun about once every 365.25 days. Is it exactly 365.25? Once every 230 million years. That's insane. Is it exactly every 230 million years? No. None of these are exact things. Say again?
Just rough estimates.
They're as close as we can get without going out like 100 decimal places. This one's 365.25. Gosh, what comes next? I don't know, pi. Some number comes after it. It's really long. All of the units of timekeeping that we're using here, none of them are actual physical quantities. The only physical time quantity is the second, because it's a certain number of oscillations of some molecule. But an hour is just multiples of seconds. You don't have to worry about that. The point is, the Earth is always moving. I once saw an animation of the Earth, quote unquote, true motion, and it had the Earth spiraling around the Sun, and the Sun was going around the galactic center, and it looked really hilarious. But you don't really have to worry about all of those motions, since motion is not absolute. Different subject. We'll talk more about that later. All right, I just wanted to introduce this to you. Also, let me show you a bit about the Earth's orientation in the solar system. We're going to end up talking a lot about this. So in this image, the Sun would be over here. There we go. There's the Sun. It's bigger than that. I was just drawing one. So here's a line directly connecting the center of the Sun and the center of the Earth. And we're going to call this the ecliptic. But by definition, the ecliptic is sorry about my terrible handwriting. The ecliptic plane is the imaginary plane created by the Earth's orbit around the Sun. So you got the Sun, you got the Earth, draw a line directly in between them. The Earth orbits around it, so that creates the plane. What we'll find later is that all of the planets orbit pretty close to the ecliptic. The only reason Earth is specifically on the ecliptic is because that's how we define it. But you'll notice the ecliptic, and then we've got this axis here that's perpendicular to the orbit. But you'll notice the Earth does not rotate around that axis. The Earth rotates around this axis. And so you'll often hear the expression that the Earth's axis is tilted. And this image helps you see what it's tilted from. It's tilted away from that perpendicular to the orbit axis. And that's going to have some pretty awesome ramifications that we're going to talk about in a bit. Questions so far? It's starting to get exciting. I think week 3 is when it gets really exciting, so look forward to that. We got another week. So here's a pretty cool question I can ask. When would I be moving the fastest? Okay, so you're on Earth, and you know that Earth takes 24 hours to rotate once around its axis. Whether I'm here, 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 or here, right? It's still going to take 24 hours for me to rotate around the axis. No problem. So, would I be moving the fastest at the equator? At the North Pole? I'm not sure. Or when it's the winter equinox. This is just a joke answer, so it's not that one. It's obviously one of these two. Okay, well, let's look at how we would figure that out. One of the things we learned someday, I don't remember which one, is that velocity is equal to the distance traveled divided by the time it takes to travel. Something like saying 50 miles per hour. That's distance divided by time. So if one of the two locations has more distance, but at the same time, it would be going faster. All right. So we're either here at the equator, or we're here at the North Pole. So at the North Pole, how far do I have to move while I'm rotating around the Earth? I don't have to move at all, right? If I'm right on the pole, this is what I'm going to do, except it's going to take me 24 hours. Yep, I just be spinning around in a small circle over the course of 24 hours. So at the North Pole, I got a small distance, same time. So we're going to make my velocity be small. But at the equator, I got to go all the way around the entire circumference of the Earth at the far distance. So I got a longer distance to go at the equator. Same amount of time, which means my velocity is higher. Does that make sense? Well, let me just say it like this. All right, right up here. At the equator, the person travels further during one day. So at the equator, during the day, during one day as the Earth rotates, you will travel further than if you're at the pole, right? A person travels further during one day than and that's pretty cool to me, because remember, the Earth is always rotating around on its axis, and you have a different velocity based on whether you're here or here. Kind of weird, right? Another way to think of it is, if there's someone who's slightly more north than you are, they're moving more slowly, even if you're both standing still. Ooh. Philosophical.
So that would be an age slower than you?
Right, but the difference is so minuscule. This is 0.00. I can't even say enough zeros. But since they are moving more slowly, then yes. So that's just to help us transition into the full lecture. Because remember, we're still talking about discovering the universe for yourself. So in order to discover the universe, we need to know where we are, how we're going, where we're going, what we're doing when we get there. Maybe not the last part. Okay, so let's figure out where we are. Well, we know we're in a classroom in Bowling Green, Kentucky, somewhere about right here. But how would you describe that to someone else? Someone's like, hey, where are you? And you're like, well, I'm in astronomy class. And they say, okay, where? And you're going to have to give them some more information, some common information. And so we have a world-used common set of coordinates. Right, two of them. One of them is latitude. That's what we're going to talk about. So I can tell you where something is by using its latitude. Take the equator. The equator is a line of latitude. It's the biggest one. And we say that the equator is at 0 degrees latitude. So all the other latitudinal locations are measured either north or south of the equator. 50 degrees north, 70 degrees south, 10 degrees south, 40. You'll notice that all of the lines of latitude are parallel to each other, meaning they never intersect. And this is the part that confused me. The lines themselves go from east to west, but that's not what they measure. They measure north and south. I'm going to draw the prime meridian on here. That's not too bad. You'll notice that it crosses the prime meridian at right angles here, 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 everywhere. And just BT dubs, it runs from 0 degrees at the equator, 90 at the poles. Just be aware of that. And you'll notice that they get shorter at the poles until at the north and south pole it's just a dot. Pretty cool. We're going to say that Bowling Green, Kentucky, we're at about, I'm going to get this wrong, 36.3 degrees north. I'm just making up numbers. 36.3 degrees north. Now that sounds good. That's some pretty deep information. But it can't be all of the story because we're not the only thing at 36.3 degrees north. In fact, well, hold on. I can make it say. Everything else on this line is also at 36.3 degrees. We have a sister city in Japan, which will be back here somewhere, also at 36.3 degrees north. So this can't be all of the story. This is why I need two properties in the coordinate system we're going to use. We got latitude and longitude. Longitude measures the distance east or west of the prime meridian. Here. And just for your information, the prime meridian is the place above which the sun is the highest at 12 o'clock on the first day of spring, or the vernal equinox. They're like, okay, well, at this location, the sun's directly above, so we're going to call that 0. But you'll notice there's some differences between longitude and latitude. Well, you'll notice that these lines aren't parallel to each other. You'll notice that the lines aren't parallel to each other. They intersect at the pole. Now, if the Earth were a cylinder, sure, they'd never intersect. But since it's a globe, they intersect at the poles. And not only that, 0 degrees here, but on the back side, completely opposite, we get 180 degrees. So we've got 0 degrees here and 180 degrees on the other side. Which means 50 degrees west, 60, 70, 80, 90, 100 degrees west. That's right. So it goes from 0 to 180. Also notice that 0 and 180 don't have a direction after it. And of course, they cross latitude at a right angle, so let me draw a latitude line. Mr. Palmer, those don't look like right angles that they're crossing at. This is a two-dimensional representation of a 3D globe. So I think I did all right. All right. So we're going to say 50, 60, 70, 80. We're going to say that Bowling Green is at 60, 70, 80, 90, maybe? Let's just say 85 degrees west. So now that we have lines of longitude, we should be able to locate absolutely anything on the surface of the Earth. Right? We should be able to locate Lexington or a coral reef over here, anything. But first, let's check to see if we were right with our location. Oh, no, not that one. I need that one. Oh, there you go. Coordinates of Bowling Green, Kentucky. .9 degrees north, 86.4 degrees west. Okay, so we weren't exact, but we were pretty close, right? Yay! Whatever, I'm impressed. Pay no attention to the fact that I did the same thing this morning and still didn't remember what it was. I can, every single time, I can't remember. I'm just like, is it 50? Is it 47? But it's somewhere around in there. So we found it. We're doing great. And this is just another image just to show the orientation of the Earth and also to show that ecliptic plane that we talked about, and to show this 23.5 degree axial tilt. And remember, if there's ever a question that says, what exactly is the Earth's axis tilted away from? We've got this ecliptic plane here. We've got this axis which is perpendicular to the plane. It is tilted away from that perpendicular axis. And this is physically meaningful. Conserving angular momentum, it would be much easier for the Earth to rotate around this axis, but it does not. It rotates around this axis. Okay, there's my page. Now, you might be wondering where I'm going with all this. What am I going to do? How does this help me with space stuff? So I'm going to do a very brief transition, which is going to help tie everything together for us. First, a pretty simple question. Have you all ever seen the moon? Yeah?
It's a bit harder to find it these days. I don't know why. I've been trying to look for it multiple nights in a row, and I just never able to see it.
It is currently, last time I saw it, it was a crescent. I want to say it was a waxing crescent-ish. Because it was over there after Sunday. Yes, I believe. Yes, sir. But I mean, in Bowling Green or Kentucky in general, the light pollution is not that terrible. We'll talk more about that later. It's just sometimes tricky to find. But we've all seen the moon. Now, think back to the last time you looked at the moon. Are you there? In your head? Okay. You're looking at it. How far away is it as you're looking at it? Did someone say far?
Yes.
That's exactly how far away it looks. It looks the arbitrary far. Which seems like the stupidest thing I've ever said, but it's scientifically true. It just looks far away. Okay, cool. Cool, that's weird, but whatever. How many of us have seen a star? Anybody? We've all seen stars? Can anyone tell me how far away that star appeared? It seems incredibly far. Does it?
Yeah. It's small inside of it.
Sure, right, but as far as distance away from you wise, it seems to be a specific exact distance of far. That's weird, right? They look the same. Here, I'll put this in a different color, so they don't look the exact same. We all know where I'm going with this, but I'm going to keep doing it anyway. All right, does everybody remember the solar eclipse? I'm sure you were outside with your eclipse glasses on, watching the moon as it covered the sun. Now, when you saw the sun, how far away did it appear to be? Did it seem to be maybe far away? And in fact, as the moon moved in front of the sun, you'll notice that the moon doesn't really go in front of the sun. It kind of looks like they just eat each other. You don't even see anything go in front of the sun. You just see part of it like do this number, to do more, this number. And once it's like about to this point, you can tell that there's some circular object in front of it. But most of the time, you can't really tell. They all look far away, which is weird. There's a physics reason why everything beyond a certain distance looks the same distance away. It's not arbitrarily, it is the distance at which light appears to move parallel, which you don't necessarily need to know that part. All you need to know is that there's some distance beyond which all things look far away. Now we're going to take that imaginary far distance and we're going to use it to construct something. We're going to construct something called the celestial sphere. I know that was a long way to go to get here, but I want to make sure that we knew why I was there. It is an imaginary and let me point this out. Imaginary. I once had someone say, "Hey, how come we can't see the celestial sphere?" I was like, "Well, it's imaginary." They're like, "Right, but why can't we see it?" And it's like, "Well, it's imaginary." So I'm going to say imaginary transparent. I don't know. I really can't spell today. There you go. An imaginary sphere surrounding the Earth on which all celestial objects lay. The moon's on the celestial sphere. The sun's on the celestial sphere. The International Space Station is on the celestial sphere. Airplanes at cruising altitude are on the celestial sphere. Noctiluminescent clouds on the celestial sphere. But as you stated, based on the size of an object, the size that an object appears can often make it appear closer but still the same distance away. I don't know. But that's a combination of an optical illusion and the celestial sphere little thing we're talking about.
Can you also like distance of like how close something is and how bright it is? Like how certain stars are like bright.
Sure. And again, even though that doesn't necessarily correlate, there's scientific reasons why we assume it correlates, and there's also like a human brain reason why you just assume brighter stuff is closer, even if it's not really. But this celestial sphere, this is completely an imaginary way to imagine stuff, right? If you look over at my celestial sphere globe, you'll notice that my globe has a celestial sphere around it. Cool. So everything in the sky appears to be the same distance, approximately, away. So if I think of there actually being a sphere surrounding the Earth, which there's not, put that out there. There isn't. I can project whatever is on the ground onto the celestial sphere. So for instance, if I am at 36 degrees north, 86 degrees west, and I look directly straight ahead to the zenith, hopefully you got that definition there, zenith, that's going to be the point directly overhead. These are my celestial coordinates. 36 north, 86 degrees west, that's a place on the ground and also in the celestial sphere. Now I can find stuff in the sky. Now I can find exactly where things are. Perhaps, say for example, Dr. Sarah's doing her observations. She sees like a super cool thing in the sky, and she wants to tell all of her astronomer buddies, and she calls them, and she's like, "Oh my goodness, there's a cool thing in the sky. Check it out." And they're like, "Where?" And she's like, "Over the barn. I don't know." She's not going to have a way to tell them where it is unless she says something like 36 degrees north, 86 degrees west. They now know exactly where to look. They can, from their location, look that direction and see it. Or if they are at that location on the ground, they can look directly up onto the celestial sphere and see it. There's another way to locate stuff we'll talk about later, but this one is my favorite.
Odd question. Is this the military use that kind of strategy?
I'm not sure.
Okay.
It would make sense. Okay. Zenith. It's a point right above your head. So anything on the ground, I can expand out to the celestial sphere. North Pole, North Celestial Pole. South Pole, South Celestial Pole. Equator, Celestial Equator, right? Do you want to do horizon here? Okay. So here's my observer, Dr. Sarah. For some reason, I always use Dr. Sarah as my observer astronomer. Notice, can she see stuff here from her location? Can she see this? The answer is no. Why not? The answer is because there's a giant planet in the way, right? She would have to be able to see through the ground. So one of the, and this is going to sound super pedantic, one of the most interesting yet basic parts of astronomy is you can't see through the ground. Which sounds stupid, but it's real. And because we are standing on a large ball, there's stuff we can't see. Who was awake last night at 11 o'clock? Anybody? Everybody's awake? Tell me, could you see the sun? No? That's because the sun was over here. You would have to have looked through the ground to see it. So this is not a concept that is foreign to us. But I just wanted to introduce the idea of the horizon and give it a little bit more concrete nature. You can consider the horizon where the ground meets the celestial sphere. That's not really what it is, obviously. It's just where you would have to be able to look through the Earth to see anymore. But your horizon determines what you can see. Your horizon determines what portion of the celestial sphere you can see. So let's put some stars up here. Here's Dr. Sarah. I'm going to put Polaris, the North Star. And I'm going to put the Southern Cross, also known as Crux, down and draw a point, right? So what do y'all think? Can she see the North Star?
Yes.
Yes, you can, right? It's right here. See, her horizon's right here, the star's here. That's about 45. So it's up pretty high too. It's at about 45 degrees.
As long as you keep the clouds above the horizon, she can see anything about it.
Sure. Everything that's up here. She can see this number, this thing over here, this.
But you can't see anything below the horizon.
Cannot see anything below the horizon. This Southern Cross here, it's under the ground, right? She will not be able to see that. But you might be thinking, well, wait a minute. Couldn't she just change longitudes and see more, right? What if she was over here? Well, she'd be able to see more stuff. Her horizon would change as the planet rotates, but there'd still be certain stuff that she could never see. In order for her to see the rest of the stuff, she would need to change latitude. So now, let me give you this next part.
So in a way, you'll always, well, you're not basically be hindered from seeing like half the celestial.
Yes.
sphere.
You're always unable to see half of it. Approximately. Latitude. Sorry about my terrible handwriting there. Your latitude. The thing about longitude is the Earth rotates, so no matter where you are longitudinally, the Earth is going to rotate around more. But if you move south or north, then you're changing your latitude, so your horizon will shift with you. Has anyone here ever been to the Southern Hemisphere? If you have not, I guarantee you have never seen the Southern Cross. It's about at the South Pole, so it can't be seen unless you're in the Southern Hemisphere. What about Boots? I think Boots is down here too. There's Boots up north. I can't remember. Boots is down there. So I don't like traveling. However, one reason I do want to travel, I want to go to the Southern Hemisphere because it's a completely different sky than what I've experienced, and I've heard it's pretty weird feeling. So I wouldn't mind. Well, weird feeling for people who always look up at stars and stuff. Questions so far? All right, let's keep going.
I do kind of have a question.
Yes, sir.
Is there a way to determine like, how to word this? Like what half of the celestial view you feel is like older and like starry than the others? Like is one younger than the other?
So you could find out, but you'd have to find the ages of everything. But I guess I should talk to you more about this later.
Yeah.
One thing we do find is that the cosmic microwave background is isotropic. It's the same everywhere. So on average, this stuff at different age, nothing. Okay. Cool. So we've got an Earth. It's tilted. We can find stuff on it. We can look up at stars. What else are we going to do with it? Who cares about this axial tilt? Well, it turns out everybody does. Let's find out more information on what this axial tilt means to us from a video I have prepared. Y'all know I love videos.
The axis of the Earth is an imaginary line on which the Earth rotates. It links up the two poles. Both the axis and the Earth are tilted at an angle of 23.5 degrees during a revolution. The tilting of the axis results in direct sunlight falling on different places during different seasons. This causes variations in the duration of days, nights, and seasons. Relationship between the location of the overhead sun and the seasons. Similarly, the revolution of the Earth and the tilting of the axis results in different angle of the sun during different periods. When the sun is directly overhead, we call this the overhead sun. At this time, the Earth's surface and the midday sun forms a 90-degree angle. Different locations of the overhead sun results in variations in the amount of solar radiation received in different areas and at different periods. Spring equinox, on the 21st or 22nd of March. The overhead sun is over the equator. The equator receives the largest amount of solar radiation. At this time, the northern hemisphere is in the spring equinox, while the southern hemisphere is in the autumn equinox. The angle of the sun decreases towards the poles. On this day, the two hemispheres receive a similar amount of solar radiation, and the length of day and night is the same at all places on the Earth. After this day, it is spring in the northern hemisphere, where the day is longer than the night. In the southern hemisphere, it becomes autumn, when the day is shorter than the night. Summer solstice. On the 21st or 22nd of June, the overhead sun is over the Tropic of Cancer. It receives the largest amount of solar radiation. At this time, the northern hemisphere is in the summer solstice, while the southern hemisphere is in the winter solstice. The angle of the sun decreases towards the poles. On this day, the length of daytime of the northern hemisphere is the longest in the year, while that of the southern hemisphere is the shortest in the year. Besides, there are 24 hours of daylight at the Arctic Circle and 24 hours of darkness at the Antarctic Circle. Autumn equinox. On the 22nd or 23rd of September, the overhead sun is over the equator again. The equator receives the largest amount of solar radiation. On this day, the northern hemisphere is in the autumn equinox, while the southern hemisphere is in the spring equinox. The angle of the sun decreases towards the poles. On this day, the two hemispheres receive a similar amount of solar radiation, and the length of day and night is the same at all places on the Earth. After this day, it is autumn in the northern hemisphere, where the day is shorter than the night. In the southern hemisphere, it becomes spring, when the day is longer than the night. Winter solstice. On the 21st and 22nd of December, the overhead sun is over the Tropic of Capricorn. It receives the largest amount of solar radiation. On this day, the northern hemisphere is in the winter solstice, while the southern hemisphere is in the summer solstice. The angle of the sun decreases towards the poles. On this day, the length of daytime in the northern hemisphere is the shortest in the year, while that of the southern hemisphere is the longest in the year. There are 24 hours of darkness at the Arctic Circle and 24 hours of daylight at the Antarctic Circle.
All right, got a point. So the whole point of this video was to show everyone that despite the fact that, yes, the Earth does move further and or closer to the sun, but not to an amount large enough to change temperature on the surface. However, the axial tilt is what ends up causing the differences in seasons. The axial tilt is what ends up causing the difference in seasons. Okay, so not the scale here, of course, but let's go over here. This is during the winter time. So remember, here's that ecliptic we were talking about. And it's tilted perpendicular to the ecliptic. So what that means is that the sun's most direct rays are incident upon this part here, the Tropic of Capricorn. This is the Tropic of Capricorn here. And it gets the most direct rays. Now you might be thinking, okay, well, how does that get the most direct rays? But think of it like this. So all the light from the sun goes everywhere, obviously. Right here, this ray goes there. Here, there's a ray that goes down towards it, and of course here, but then there's some rays that don't hit the earth, right? So if we just take all these rays, they all focus on right here. So this is getting the most direct light. That wasn't the best explanation, but that's how I think of it. Of course, during the northern summer, the sun is directly above the Tropic of Cancer, here. And so over the course of the year, the sun and its highest place goes from here to here to back here. So on average, the equator receives the most sun, or the most direct sun. So this is the warmest area of the planet.
Why do they name certain like tropic like that, like tropic of Cancer, tropic of Capricorn? Why do they name them?
Zodiac signs. And there's other reasons that I can't think of right now. The Aries point. It has to do with the sun's position in front of one of the zodiac constellations. The zodiac constellations are the constellations that are on the ecliptic, so they go around this area. We'll talk more about constellations in a moment. So just remember, axial tilt causing seasons. If there were less tilt, the seasons would be less extreme. If there were more tilt, the seasons would be more extreme. So, if you go closer towards the equator, you'll notice that it doesn't really have seasons so much. There's hot season, and then there's a hot and wet season, maybe. But if you go to the southern hemisphere, you'll notice that you start to get seasons again. And the difference betwixt the two seasons is a little more extreme than it is in the northern hemisphere. And that's because during southern summer, the sun is actually a little bit closer, like 3 million miles. It doesn't matter. Not too much. All right, just two more things I want to point out before we get out of here today. How are y'all feeling? Y'all feeling all right? Still awake?
Yeah.
Awesome. Nice. Well, in that case, we're going to do a little bit more participation. Someone please tell me one constellation that you know of. I hear Big Dipper. I'm going to write that up here. Anybody else got another one? I got a Little Dipper. That's L-I-L. Anything else? That's good enough. We'll take these two. Now I'm going to draw them, and you have to make sure and tell me if I'm doing it right. So let's draw the Big Dipper. Pretty good? Okay. Now I'm going to draw the Little Dipper.
How do you read the dots?
Yeah. Well, they should be, right? They're dim stars. I'll make Polaris slightly bigger. Which should be... Whoops. Hey, I almost did. That's not too bad. All right, so we got the Big Dipper and Little Dipper there, and these are the two constellations that we know. What if I told you that these are not constellations, despite the fact that we colloquially call them constellations? In fact, if we're speaking scientifically, which why would we be in common usage, we would have to call them asterisms. An asterism is a group of stars in the celestial sphere said to make a shape or form a pattern.
Basically, we should just replace the word constellation with asteroid.
In common conversation, I would just leave it the same.
Okay.
I'm just giving you the scientific version of the terms. Another interesting piece of an asterism is that they're culturally determined. So our Big Dipper doesn't necessarily mean something to other folks in other cultures, right? We've been told that that shape is there, but it's not really there. It looks like it's there. There is an asterism, and I can never remember what culture it's from or exactly what it's called. I want to say Seventh Gate Turtle or something. Because it has a star, there's two stars here, and a star in the middle. It's supposed to look like a diamondback turtle looking from top down. We don't have the cultural reference for that. We don't have that asterism. So usually when we think of the term constellation, we think of the asterism within. All right. I want to draw another popular asterism. We're going to do some stuff with it. That's right. I think I put Beetlejuice in the wrong place. Whatever. All right, so this is another asterism that we talk about often. Orion. But you may be like, I have certainly been told that Orion is a constellation. And now Mr. Palmer is saying that it's not a constellation. It is a constellation. Let me draw the constellation of Orion. Okay, I'm not going to mess it up. I got this one. I know I messed up that one. There. Everything within this space is the constellation of Orion. We think of the asterism within, but in reality, this whole area is a constellation. So let me give you the scientific definition of constellation. It is a specific region of the celestial sphere. And the constellations were decided upon by the International Astronomy Union. International Astronomy Union. So any star in here, whether it's bright, dim, whether it's part of the asterism, whether it can't be seen or can. Anything that would appear right here is in the constellation of Orion. You may see something written like this. Trying to think of a specific stuff. It says Ori Delta. So that would be the fourth brightest star in that constellation. Even if you can't see it, even if you don't know where it is, let me draw another star. That's part of the constellation. Does it make the asterism? No, but it's still in that constellation. Pretty cool, right? So when you say Big Dipper, what you want to think is Ursa Major. Ursa Major is the constellation. It is, I want to say it's the biggest one, but that's not true. I'm going to look that up later. You want to say Ursa Major. Ursa Major is a constellation. The Big Dipper is an asterism within that constellation. So when you get to a question later, the question may ask you something like, what is the brightest star in the Big Dipper, or something like that. So then you have to think, is it giving me the brightest star in the asterism of the Big Dipper, or telling me the brightest star in the whole constellation? Might be a trick question. Okay, so there are 88 constellations. There are exactly 88 constellations. The background of these constellations comes from a combination of cultures and scientific histories, which is why we all have to agree on them. 13 of those constellations are the zodiac constellations. I'll let you learn more about that later. There's such a large argument about the zodiac constellations. And I'm going to have to take a brief segue. We got time to tell you about this.
Yeah, I'm not sound like I'm going like you're like what the
Well, the scientific argument about the zodiac signs is that the constellations, the zodiac constellations, they are the constellations that are on the ecliptic. So they're the constellations that are on the ecliptic. And it's usually considered that there are 12 of them. But here's the problem, right? Okay, let's just say I drew 12 boxes, right? But you'll notice that there's a small gap between two of the boxes, and there's another box that kind of fits there-ish, right? This should also be a zodiac constellation, which is why you will hear people say that there are 13 of them, right? But gosh, it's such a big fight between whether there are 12 or 13 zodiac constellations. There's also the astrological fight, which who cares? Well, I care, but you know what I'm saying. This is more of a fight between, do we consider this one, which does not fit the same pattern, one of these things?
Why is there a gap?
Why did we do that? I actually don't know. I can't think of a good reason. The asterism for what is it? Scorpio and Capricorn left like a little space between here. And I think originally Ophiuchus was counted but then it was like got rid of because we have 12 months. So I don't know.
Oh, okay. So I guess that's what I kind of consider like controversial because there's not 13 months.
Right.
There's only 12.
Yes.
That makes sense.
And a lot of folks were like, "Oh no, it's going to change my astrological sign." And I'm just like,
I mean, you
Does
can
it?
easily assign two zodiacs for 1 month. Like one
Well-
month has one. Then later half has another.
as much as I would like to go off on that, I'm gonna leave it for now. All right, one last thing, guys. This is it, y'all. Y'all excited about this last bit of information? Let's get hype! Woo! I'm sorry. I don't know. That's my ecliptic. We talked about this perpendicular axis and how it would be easier for the Earth to rotate around that axis, but how the Earth just ain't having that. Well, in the end, physics wins. So there must be some sort of compromise. This axial tilt is not this. This is the easy one. This is what we actually have. So the compromise between the axial tilt that's expected and the axial tilt the Earth actually has is for the Earth's rotation axis to actually rotate around this, the precessional axis. So the Earth, imagine spinning a top, right? You know how eventually it starts like wobbling and then falls over? Well, imagine the Earth is going to start like rotating. It's not going to fall over, right? But the pole rotates around, meaning that 2,000 years ago, the North Star would not have been the North Star. And in 13,000 years, the North Star will be something different, if anything.
You said the rotation of the Earth is like slowing down very, very, very slowly.
It is. And I can talk about that as well. All right, so here's where we are now. Hilarious. But as it moves, as the Earth processes, the North Star is going to change. It'll be nothing for a while, right? Be nothing. And then we get about to maybe AD 7700, which is a real year that will actually happen, by the way. I don't know if that's hard to deal with or not, but that's a real year. The North Star, or the closest, will be this one here, but not exactly. So that's pretty cool, right? You may have heard the idea of the age of Aquarius. That just talks about the precession of the Earth. Google it more if you want to know more about it. It's pretty interesting. So just remember, precession is the rotation of the Earth's rotational axis around the precessional axis. Luckily, our 23.5 degree tilt is approximately stable, small variations, because we got a giant moon. Any questions? I can't believe I've been talking for an hour and 20 minutes already. Hour and 10 minutes. That's it. Have a nice week. Thank you very much. I appreciate it. Yay. And now get this video uploaded ASAP. Don't forget your journals.